unprecedented scientific, or should I say engineering breakthrough, unprecedented breakthrough in the field of clean energy, unlimited clean energy known as fusion. Ladies and gentlemen, there's been a big breakthrough in that regard. You may have heard of fusion before, but let's go ahead and see what's going on here. Basically, December 13th, 2022, Energy Secretary Jennifer Granholm announced that scientists at the Lawrence Livermore National Laboratory in California achieved fusion ignition, which she described as creating more from a fusion reaction than the energy that was used to start the process. Okay, we have already known about fusion in terms of scientifically. Fusion is what the sun does, it's what stars do, taking two pieces of hydrogen, smashing them together, creating helium, and energy is released. But the thing is, we have not been able to get more energy out of it than the energy that we initially put in, okay, used to start the process. She called this breakthrough, which occurred in December 5th, 2022, one of the most impressive scientific feats of the 21st century. Secretary Granholm further explained the importance of this achievement and the implications to the clean energy space. Okay, ladies and gentlemen, let's get right into it. What is this fusion thing that we're talking about? What exactly is fusion? Fusion, as I mentioned, is what goes on in the stars. And our local star here in our local solar system is the sun. That's what we call it. We call it the sun. And the sun takes two hydrogens, smashes them together, creates helium. Okay, hydrogen is basically has one electron, smashes them together, creates helium, which has two electrons. Helium is at a lower energy state than the hydrogen that you started out with, so there's excess energy which gets released. So basically, as a result of taking two pieces of hydrogen, which are at a higher energy state, smashing them together than the resulting helium, which is at a lower energy state, there is energy released, shown right here. But in order to create this fusion right here, in order to fuse the two hydrogens together, we need energy. Right? We need to use these lasers and focus these lasers, right? And create enough energy to fuse the two hydrogens together. And that energy that you use to fuse the hydrogens together needs to be less than the energy that is released for this to be a viable energy source. Okay. Now, how does the sun do it? The sun does this by basically gravity. Okay, the sun is massive, so it's got a lot of gravitational help, a lot of gravitational force fusing the hydrogens together. But we don't have the gravitational power of the sun. So how can we create all this unlimited energy? That is the question. And we've just crossed the particular threshold, ladies and gentlemen. So let's go ahead and play a little clip from one of the scientists here, basically elaborating on what I just described to you regarding the fusion process.
The National Ignition Facility is the world's largest and most energetic laser system. During experiments, 192 high-energy lasers converge on a target about the size of a peppercorn, heating a capsule of deuterium and tritium to over 3.
Deuterium and tritium are the two isotopes of hydrogen. Those are just basically two hydrogen elements of different nuclear composition. Okay, they have different composition of nuclear protons in protons and or neutrons in the nucleus. Okay, so as we mentioned, we're fusing two hydrogens together, creating helium, and also this energy that's released. This is what is done by the sun. The sun does it because it has massive gravitational energy, because it's massive, it's huge, and it's squeezing those hydrogens together. We are doing it by concentrating these lasers together at a point, heating it up.
Lasers converge on a target about the size of a peppercorn, heating a capsule of deuterium and tritium to over 3 million degrees Celsius, and briefly simulating the conditions of a star. In achieving ignition, the researchers at Lawrence Livermore have opened a new chapter in NNSA's Science-Based Stockpile Stewardship Program, enabling us to study new regimes. Along with this, we have taken the first tentative steps towards a clean energy source that could revolutionize the world. Earlier this year, I had the opportunity to remember the 30th anniversary of Divider, the last explosives nuclear weapons test conducted by the United States. And reflecting on Divider, I spoke of how far our stockpile stewardship program has come, and in how many ways we now understand our nuclear weapons better than we did when we were testing.
All right, ladies and gentlemen, as I mentioned, the threshold that was crossed is the fact that we can now get more energy out of the fusion reaction than we used, okay, to get that. However, there might be some questions, okay, some engineering and scientific quibbles with regards to that, because basically the laser pulled about, what is it, 300 units of energy. I forget which particular units we're talking about now. Let me go ahead and check my trusty system here. 300 megajoules got pulled out from the energy grid. And we got about 300 megajoules out of the system as well. But in reality, okay, that is not a very efficient thing, number one, because, you know, it's almost 1-to-1. But in reality, more energy was used because there's systems behind the grid. Okay, there's systems, okay, used to power the grid, and think about the workers and the people doing the things. Okay, energy is being put into that grid system, and in order to create that 300 megajoules, and then that was pulled out. But now we're saying that we've crossed a particular threshold. Either way, it's more than anyone else has been able to do. Let's hear a little bit more, okay, from the Secretary on this.
It's a scientific breakthrough that it says will pave the way for production of cleaner energy. In a news conference, Energy Secretary Jennifer Granholm talks about how scientists have, for the first time.
Well, let's see here. Let us see. Because one of the main things is about the scalability and the investments that we're going to get as a result of this. Okay, the scalability and the investments.
Hey there, Secretary. Gary Grumback from NBC News here. There's questions about the ability to scale here, and that was touched on a little bit as it relates to power plants, et cetera. But can you talk about the ability to scale and who should be in charge of that scaling? Private, government, both?
Well, clearly we want the private sector, we need the private sector to get in the game. Though it's really important that there has been this incredible amount of US public dollars going into this breakthrough. But all of the steps that we'll take that will be necessary to get this to commercial level will still require public research and private research. We know that there's been a huge interest among the private funding community, startups, et cetera, and we encourage that. The president has a decadal vision to get to a commercial fusion reactor within, obviously 10 years.
So this announcement, okay, is part of a marketing ploy, if you want to look at it in a cynical view, a marketing ploy to encourage, the billionaires out there, the hedge funds, no, not necessarily hedge funds. We're talking about venture capital. We're trying to bring venture capital into scientific and engineering space to invest. Okay, my man Peter Thiel has a lot of investment in this particular space, in the energy space in general, but also in fusion. These are things whereby you're throwing money into a system and you don't know whether you're going to get the money, whether you're going to get a product that works. Okay, for the next 10 years, you don't know. There is no product market fit, and then you can then iterate. It's not like, oh, I make the first model of the Tesla, I take it out into the market, I see how it works, I use the money that I got from selling the first model of the Tesla to make the next model and the next model and the next model. In groundbreaking scientific research such as this, it is very difficult to know exactly what the first model or the first working model is. What will be the first kinds of systems that actually do work? So it is a difficult thing to know. Should I put my money in now? Okay, should I wait till later? So making announcements such as this saying, hey, we've gotten to a particular breakthrough, which again is kind of questionable, as I mentioned before, regarding the 300 megajoules that was pulled from the power grid used by those lasers to heat up the hydrogen isotopes, okay, and then to create the helium and create that energy. The fact is, we need to have these kinds of announcements and, to kind of bring in some fresh excitement and enthusiasm and, yes, money into the system so that the private people can take over and so that the government is not completely burdened with the task of this kind of research.
So we've got to get to work, and this shows that it can be done, which has been a question. Can you get there? This demonstrates it can be done. That threshold being crossed allows them to start working on better lasers, more efficient lasers, on better containment capsules, et cetera, the things that are necessary to allow it to be modularized and taken to commercial scale.
Scalability, modularized, and scale. So let's go back to this thing that we shared here before. Okay, remember the whole process which goes on in stars in the sun is you take two isotopes of hydrogen, just basically two types of hydrogen, okay, called deuterium and tritium or whatever it is. Okay, two hydrogen atoms smashed together, you create helium and you get energy out of it. Now, in order for you to do this smashing that's going on here, you need a lot of energy. How does the sun do it? The sun does it because it has a lot of gravitational energy because it's massive. But in our situation, what we need